reason. Andrew does everything. I asked him how to introduce himself or how I would introduce him, and he was like, I don't know, just say that I do things, which made it sound like a hobo came in off the street. So this really nice hobo showed up with his PowerPoint presentation, and I was like, hell yeah. But for real, Andrew speaks all over town. He's amazing. I accosted him after I heard him speak, and he was kind enough to come here and talk to you guys. He also teaches a class in fun at an academic level at the University of Colorado, Denver. So, if that is not, this guy, right? If that's not enough of an expertise, I don't know what is. So, with no further ado, Andrew.
Get serious now. We got all that funny stuff out of the way. We're going to get really serious and talk about. Does everyone know what GPS is? First of all, it's global positioning system. It's what's in your phone. It's what's in your. It's in a lot of things that help you see where you are. It's in your car. So global positioning system. It's a bunch of satellites, and so I want to talk about how it works because. In talking with people, everyone's like, oh, my GPS is broken or whatever. Like, no one knows really how it works as far as that I've come across. But in order to explain it, I want to invoke Flav. All right, so Flavor is going to help explain GPS. All right, you can pump up that audio because I'm not going to be talking during it. So what is GPS? It's a positioning and navigation service with up to 32 satellites. There's actually even more satellites, but there's slots in the data for 32 satellites. And so, oops, that was not the right button. Where's my pointer? Oh yeah, there we go. So these satellites are precessing around the globe in 6 different orbital planes, and so they really are covering 99.9% of the globe. So anywhere on Earth, and that's one of the reasons why GPS is so great, is because you could get it from anywhere on Earth. There's semi-synchronous orbits. Does anybody know what that is? Sort of synchronous, yes. It's like semi-sweet chocolate chips, but orbiting. Now semi in this case means half. They're actually at half a geosynchronous orbit. So like a satellite that, say like your DirecTV or something like that, where you put a dish on the side of your house and you just point it once and it always gets the satellite, that satellite is called geosynchronous orbit. So it's always in the same place in the sky. So as the Earth goes around, it's always the same. So a semi-synchronous orbit is it's half the altitude of a synchronous orbit. So it actually goes around the globe twice per day. So any particular satellite will actually pass overhead twice, and they're actually moving fairly fast because they go around the Earth twice in a day. So and it's 20,000 kilometers.
Yo, we got to get stupid. Yo.
All right, let's get stupid with some satellite nerd talk here. So. The first GPS satellite was launched in 1978, and it's a Department of Defense system. It's a US DOD, super scary military stuff. And they basically just want to use it for positioning. It's not for spying. A lot of people think, like, oh, I'm not going to put my GPS on because I don't want the government to know where I am. But it's actually a one-way system. So these satellites are sending data in kind of a wide band direction towards Earth. So when you're receiving the data, you're not actually sending any data anywhere. So unless you have some app on your phone that someone who wants to stalk you put on your phone without you knowing, and it sends out the information about GPS. But the US government doesn't know where you are based on GPS. But when they put a few satellites up in the air, but it really doesn't do that much good if you only have a few satellites. You need to have a lot of satellites, and so you get information from a lot of satellites at the same time, and that's how you get your positioning. So they started building this constellation, and these things cost billions and billions of dollars, and it takes years to make them. But a lot of them were made in Colorado, right here in South Denver at Lockheed Martin. The whole Block 2 and 2R satellites during that time range. And so what they do, they basically broadcast data. That's just what they do. They broadcast data at 1500 megahertz. There's two frequencies actually, there's L1 and L2. I think I might talk about that a little. But it's encrypted data with two different kinds of codes of it. And so there's a CA code and a P code. And so the CA code is something that is used for civilian use. So if it's in your phone, it's CA code. You need military clearance to run a P code receiver. But what happened in the 90s, so it had full operational capability. So in the 90s, they started building it into things. It's in a car, you can have it handheld, and then, more recently, cell phones and things. And so it's now, it really is, the government is running a civilian service now. So how does it work? Flav is gonna help. So these satellites basically broadcast their position. Every second they send out a big chunk of data at a fairly high data rate, and they're sending out a bunch of information. One is their position. There's a lot of things about which orbital plane they're on, what part of the troposphere they are around, their speed, because they're moving pretty fast. And so the users receive the messages from the satellite.
Yo, we got to do something about that, man. Yo, we got to be stupid. Yo, we got to let them know what time it is.
We got to know what time it is, which is the crux of how GPS satellites work. You get all this information from all these satellites that you can see overhead, and they all have atomic clocks on board, and they're all synchronized to each other within probably 20 nanoseconds, so 20 billionths of a second. And so they're broadcasting where they are, and they're all broadcasting at the same time. But being here on Earth, you're actually going to get a signal sooner from one that's directly overhead than one that's on the horizon, because it has to go a lot further. So every second, you get information from 5 to up to 12 satellites. And you get it, even though they send it at the same time, you actually get the data at slightly different times from each other. And so you gather all that data, and with microprocessor, you start to figure out where you are on the globe. So it all has to do with atomic clocks. I've done some other talks about. Has anyone seen any talks I've done about atomic clocks? Yeah, if you ask me something about it, I may never stop talking. So just be careful what you wish for. I should say, maybe I'll intro myself a little. I actually work at the National Institute of Standards and Technology, measuring atomic clocks. So that's my day job. So that's the official government standards lab, and I'm in the time and frequency department. So we're measuring atomic clocks remotely. We use GPS every day, comparing atomic clocks or comparing ground-based clocks using GPS as a transfer mechanism. So it's very cool. So when a satellite, or when anything, a radio station, a walkie-talkie, something that sends out a frequency, it travels at roughly the speed of light. And it does have to go through like the ionosphere, the troposphere, gets noisy, can change the speed. But we can say that that a radio frequency signal basically travels at the speed of light. And so a 1 meter is equivalent to 3.3 nanoseconds. We always say like a nanosecond a foot. It's a rough estimate, but so you can see where you really need to be able to distinguish nanoseconds in order to get close even to like a meter of positioning. Oh man, I got super nerdy here when I said 1 part in 10 to the 13th stability. That's like clock talk. But there's all sorts of different equations that come in with comparing clocks, and we talk about stability, and there's this whole new set of math talking about something, because all clocks are changing in frequency all the time. I don't know if you knew that, but so this is let's just say this is really good. like 13 decimal places of stability. Oh, whoops, I meant to start that earlier while I was talking, so you could be like mesmerized by the atomic clock. So let's talk about some equations here, pseudo-range calculation. I almost every talk that I do, I feel like I throw an equation up there because it's just, everyone gets nervous and they're like, oh, okay, I'm gonna get a drink, this sucks. I don't wanna learn anything, I just wanna like see something. So I'm not really gonna talk too much about this, but c is the speed of light, that's something. This is the ionosphere, the troposphere, but basically you have to, when you get the signal from all these different satellites, you have to reiterate it for each satellite and multiple times and go through this equation to get the pseudo range, which in the end tells you where you are, latitude, longitude, and altitude. Out there that's helping us out. So these are all the monitoring stations for the satellites, and these are all U.S. government, government posse. And as the satellites go overhead, all these stations are measuring compared to ground-based clocks, and they're actually comparing all of the satellite clocks to each other. There's a really big benefit if you actually already have your position. So if you have like a set position, like you're not moving. Then, when you gather information from the satellites and it's giving you this pseudo-range information, since you know where you are, you can actually hone in on what's happening with the clocks on the satellites. And we can actually measure the satellite clocks on a ground-based station because we're not moving. And we know the right answer of like what our position is. So as the satellites go overhead, and these ground stations are measuring and adding corrections to the satellites, and they're moving fairly quickly. And if you know anything about relativity, you will know that frequency and motion are tied together with time dilation. So there actually is a pretty high relativistic effect of the clocks on board the satellites. You need to correct that all out. The main control station is actually at Stryker Air Force Base in Colorado Springs. So Colorado actually has a pretty big part of GPS in several ways. All the clocks are run by the USNO, it's a US Naval Observatory in Washington, D.C. So spread spectrum communication. Also, I'm not going to explain. So spread spectrum is a way of communication where instead of having like a signal at like a particular frequency range, the data is actually spread across a wide range, and it actually helps with spoofing and jamming and things. But it's also, the signal is really far down in the noise. So you really are fighting the power. I mean, these things are 20,000 kilometers away, sending you a radio frequency, and in this world of all these frequencies flying around, it's kind of hard to get the satellites. And that's another thing I'll point out, Mythbuster here. So when you see on TV and there's like, they're following, like on CSI or Law and Order or something, they're following somebody, inside of a house or a parking garage, like, first of all, I don't know how they know where that person is, because even if that person had like a GPS, they're not telling the cops where they are. But also, you have to have a sky view, so you have to actually be basically outside. You could put a GPS antenna in a window, but you're only going to see the satellites that are on that side. It would be pretty hard to find too good of a position, even through a window. So, because it's very low power. A radio station, like a local, KBPI type radio station, is a very high power and it's very localized. That's why you can get it through walls and windows and things. So you really can't get GPS inside at this point. But it's also because of how they're trying to really hide the signal in the noise. So it was by design, because really, like, we want to use it, but we don't want other bad guys to use it. So it's a military system. So selective availability. So when the military, when they started using this, they they want to have. They realize that other people can get it, right? But they actually put noise on the signal to make it worse for civilian use. So that's called selective availability, where they could actually turn up the noise. So it's pretty cool. You know where this is going? Bring the noise! Bring the noise! So they brought the noise over. And so this is actual data of all the cells, and with selective availability off. And you can actually see your range is really within probably a 50 nanosecond band there. So you know your positioning can be good. But when you have selective availability on, it's actually much worse, and you have to have a P-code receiver in order to take this, what looks like random noise is actually encrypted. But since it really became such a high use for civilians, I think Al Gore was actually part of this, but they actually got them to turn selective availability off. So it was in year 2000, I think March or April in year 2000, they turned selective availability off to actually make it better for positioning for civilian use. So Flav is super happy about that. So that's how we can get such good positioning. And you can, if you average for a fairly long time, I'd say you could get within maybe 10 meters. And so there again, like if you hear like, oh, I moved 2 feet and my GPS told me, it's actually relative. So it can tell which direction you're moving. Your actual position is not that good. But there are enhancement systems, so it's called differential GPS. So if you have like a known point, like a surveyed point, and that's receiving GPS, but because remember I said, if you know where you are, you can actually see the GPS noise. So like at a construction site, you'll see like in a magazine, super nerdy magazine by the way, but like the GPS magazine where they advertise like, we put a GPS receiver on the edge of an earth mover, and we're like doing precise earth moving, and I'm like, that's not even possible. But differential GPS, so they have a ground-based station that's stationary, and because it knows where it is and can see the GPS noise, it actually broadcasts a local signal and enhances the GPS because your position looks like you're moving around when you're not. So since that's not moving, even if you are moving, you have this enhancement system, it actually subtracts that noise out, and you can actually get within 20 centimeters of position, so not bad. So thank you, and thanks Flav. I hope you guys learned a little bit about GPS. I don't even know what time it is. Am I ahead or am I behind? All right, and I know you think I'm super nerdy, so just to prove that I'm cool, I'm going to show you a video. And this is, so my boss comes up to me, and he says, hey, do you know this guy named Flavor Flav? I've heard of him, and he's like, well, they're doing on Comedy Central, they're doing this roast of Flavor Flav, and so they're asking people to submit like their own roast videos for Flavor Flav, and they're gonna pick the best ones, and they're gonna show them on this Comedy Central roast show. So he's like, that's the guy with the clock, right? Is that the guy with the clock? I'm like, yeah, that's the guy with the clock. So he's like, well, we're the guys with the clocks. Like, we should make a video. He's like, he doesn't know what time it is. Like, we know what time it is. basically about where we were in atomic clocks with Flav. So here it is.
Yo, Flav, public enemy number one in Boulder, Colorado. Hello, Mr. Flav. I understand that you're interested in the subject of time. You don't know what time it is. We're standing here at the National Institute of Standards and Technology in Boulder, Colorado, the official timekeepers for the United States. Got some non-believers out there. Come on inside, I'll show you around. This is an atomic clock, one of the most accurate timepieces in the whole wide world. Like to see you hang this around your neck. Yeah, boy. By international agreement, the second is now defined by the hyperfine transition of a cesium-133 atom. That is 9192631770 cycles per second.
9192631770 is not a joke in this town.
If you were so sophisticated, you would have a radio receipt clock that sets itself to the correct time. Have a nice weenie roast, Mr. Flav.
Thank you everybody for coming. Thanks, Sarah. She always puts together an awesome program. Oh, questions. Okay. It's not over yet. Apparently, we got some questions. So, let's see. Over here on the edge there.
Yeah, you said something about clocks changing frequency all the time, and I'm just curious what you meant by that. I think about clocks being like 60 hertz or something.
Yeah, so anything that generates a frequency, whether it's, time is based on the rotation of the Earth. It was something that was very periodic, right? But then when better clocks came around, they realized, oh, the Earth isn't really that periodic. It's actually, the rotation of the Earth is changing. But now we have good clocks, we can actually measure the rotation of the Earth. And then come up with better clocks, and we're like, oh wait, those clocks are actually changing. So something like the quartz crystal in your watch, it's set to a certain frequency. It's actually 32.768 kilohertz, which is easy to divide out by 2 several times digitally to be 1 second. And so it's set at that frequency, but it's set at that frequency in some factory somewhere, and it's actually moving off that frequency based on temperature, it's based on just time, it's just aging. So by the end of the lifetime of your watch, it's actually fairly far off of its set frequency. So even an atomic clock, we're basically locking quartz crystal clocks to a transition of an atom, which is actually much, much, much more stable than a man-made clock, because we're getting a frequency from an atom. But even cesium atoms have a frequency range, so it's a Gaussian distribution of frequency, and they are changing. So yeah, all frequencies are changing. I'll stand by that. Who over here was standing up? Yeah, very excited.
First, I was going to ask if it could tell me if 911, if I dialed it a long time ago, but then.
If tell you what?
If GPS could tell me I dialed 911 a long time ago, but that was a Flavor Flav reference.
Oh, yeah.
And then I was going to ask if you could tell me the time I got to Arizona, but that was another Public Enemy reference. But my real question is, why does my phone tell me to turn on my Wi-Fi to improve my location?
So if you have your GPS turned off, say, let's start out with that. Your phone actually tells you where you are to some degree. It might be like a mile away, but it's actually using like triangulation or quadrangulation from cell phone towers. So the cell phone towers know their position, and when they're broadcasting as part of the message as you're handshaking communication data with the cell phone tower. So when you start getting information from several cell phone towers, your phone is actually helping locate you. If you have that also with GPS, so augmented GPS is basically using the cell phone positioning, augmenting GPS. So if you move like 5 feet this way, you're closer to that cell phone tower, and the power of that cell phone tower is a little bit stronger. And so it actually does kind of augment GPS like indoors. Because once you went indoors, your GPS kind of lost it, but you still are getting the cell phone tower signal. And I will also add that your cell phone clock is set by the base. It's not set by GPS, even though you have GPS in your phone. They should. It actually comes from cell phone towers, but the cell phone towers oscillators are actually synchronized and steered by GPS. And in a cell phone tower, this is an aside, but in a cell phone tower, the better the frequency, the more data you can pack in. So, in other words, they need better and better clocks, and that's why GPS is so great for cell phone towers, because they can have a very stable clock steered to GPS, and that's how so many people can be on the phone at the same time and transmitting all this data. So atomic clocks are really, they're behind the scenes, but they're ubiquitous. It's like all of these things, if GPS went away, there's really no backup to it. So it's pretty scary because, so something like cell phones, that's like, cell phones will quit working probably within 20 minutes of like a GPS outage because the clocks will just be free running, the base station, that you can't carry all the data, the bandwidth isn't good enough. Some more questions over here.
Yeah, you said that the international standard is now the CC map, and that's 1 in 10 to 13, but when does that come for review and what do you think is going to replace it?
That's a good question. Yes, so the cesium atom, the 9192631770 hertz, is the standard definition of the second. And to change a definition, it takes many, many years of international agreement. And you would really have to have a commercial clock for some other kind of atom so that people could actually realize the second in their own way in the laboratory. Right now at work, we're using strontium. Is a possibility, aluminum, ions, so charged particles, calcium is up there, ytterbium. The reason we use cesium, it has one valence electron, it's very stable, it doesn't decay and change orbital state, so we actually interrogate it with a frequency. So we can actually trap single ions and hit them with different frequencies and make them change atomic states. And some of the people from this research are actually building quantum computers, which is basically using single atoms as logic gates because they can turn them on and off different states. So it's pretty mind-blowing. We have time for one more question. Here in the front. Okay.
Why did they put these GPS satellites into a semi-synchronous orbit instead of going all the way to a geosynchronous orbit?
For coverage, if you like a geosynchronous satellite, it showers down a frequency on Earth, but it's not enough coverage. If they're moving, there's always ones moving into view as other ones are moving out of view, and so it has more of a coverage. You would have to put these synchronous ones like above, like Alaska, even though like there's not as much use above Alaska, so you're gonna have to put a satellite there to hit that part of the country. And then do you put one on the North Pole or not? Like no one's up there or whatever. So it's a way to be sure that the entire globe is covered. You would have nulls and outages in different areas. So I'll be around all night, whatever, if you guys want to ask questions, or I have a website, isaveeverything.com. We didn't talk about that, but look it up.